Hello friends, here in this video we are going to see the expression for efficiency of a diesel cycle. That is, we are going to derive an equation here. So it is called as expression for efficiency of diesel cycle. Now see, when we are deriving the equation for the efficiency of diesel cycle, in that the first thing we should have is PV and TS diagram, that is pressure and volume diagram and temperature entropy diagram, so that we can move further into the derivation part. So here I'll start this derivation with the PV and TS diagram. Now when I am drawing the PV and TS diagram, the first process in case of diesel cycle is isentropic. It is also called as reversible adiabatic compression process. So that I'll show it onto the PV diagram. Here this is process 1 to 2. Now this indicates isentropic compression, and as we see in this diagram, during the compression process at point number 1 the volume V1 is more, at point 2 the volume V2 is less. It means during the reversible adiabatic or isentropic compression process, volume decreases from V1 to V2 but pressure increases from P1 to P2. Next, after the compression process, that is reversible adiabatic or isentropic compression process, the second process in case of diesel cycle is constant pressure heat addition. So here, keeping the pressure constant, we are going to add on heat, and that will result in increase in the volume. So here I'll denote 2 to 3 as a constant pressure line. So I can say that pressure at point 2 and pressure at point 3, they are same. So this is the heat addition process from 2 to 3. Next, after this, process 3 to 4 will be isentropic expansion. That is, once the heat has been added from point 2 to point 3, next there will be the expansion process, and that will also be reversible adiabatic, that is isentropic expansion. So this is process 3 to 4 in which we are getting reversible adiabatic, or we can say expansion process. Now during the expansion process, volume increases from V3 up to V4. At point 3 the volume is V3 and here the volume is V4. And after the expansion process has been completed, next there is heat rejection, and in case of diesel cycle the heat is rejected at constant volume. So it will be rejected from point 4 to 1 at constant volume, and we can see that V1 is equal to V4. Next, as we have shown all the processes on PV diagram, next I'll show all the processes on temperature entropy, that is TS diagram. So here process 1 to 2 is isentropic compression. So isentropic compression will be shown on TS diagram with a vertical line. It is, and it will be of increasing nature, means that during compression process the temperature will go on increasing. So here process 1 to 2 indicates isentropic compression, wherein we can say that the entropy remains constant. So S1 is equal to S2 and temperature is increased from T1 to T2. Next, after isentropic compression, the process is 2 to 3, which is constant pressure heat addition. So constant pressure heat addition line, it will lie on a constant pressure line which I am drawing here. this is a constant pressure line, P is equal to constant. Now the heat will be added on this line, that is at constant pressure, from 2 to 3. So heat will be added and temperature will go on increasing, along with that entropy will also increase. So we reach point 3, that is constant pressure heat addition. Now if we see over this line of constant pressure, pressure at point number 2 and pressure at point number 3 both are same, that is at constant pressure. Next, after this 3 to 4 was isentropic expansion. So for isentropic expansion, the entropy again should remain constant and there should be drop in temperature. So from 3 to 4, here we arrive at isentropic expansion, and as we see the entropy remains constant, that is S3 is equal to S4, but the temperature drops, that is temperature is dropping during the expansion process. Now after this, process 4 to 1 is constant volume heat rejection. So I have to draw a constant volume line. So here I will draw a constant volume line joining point 1 and 4. Now this constant volume line will be slightly more inclined compared to the constant pressure line. Constant pressure lines are less inclined compared to the constant volume line, and then we see when the heat is rejected, temperature will go on decreasing and even entropy will decrease. So we will come from point number 4 up to point number 1. So this is the decrease in temperature, and at the same time there is decrease in entropy from point 4 to point number 1. So this is the heat rejection process, and the volume of point 1 and point 4, they are same because they lie on the same constant volume line. Next, over this diagram from 1 to 2 it was compression, so work which is done in compression. Next, from 2 to 3 the heat was added into the system, so heat is added at constant volume. During 3 to 4, the work we are getting from the system, that is work we are getting during expansion process. 4 to 1, the heat is rejected out of the system, so it is Q suffix R. Similarly, these processes can be shown on the TS diagram. From 1 to 2 we are getting, or we can say that work is input, that is work done in compression. From 2 to 3 heat is added into the system, so it is Q suffix A, heat added. 3 to 4 it is expansion, and 4 to 1 it is heat rejection, that is at constant volume. So I have shown all the processes on PV and TS diagram. This was the starting step for efficiency of diesel cycle. Next, I'll say that consider mass of air, that is small m, is equal to 1 kg. That is the assumption for us. Here we are assuming, in case of the derivation of diesel cycle, that the mass of air which comes inside the engine, it is 1 kg, and that we are going to keep it as constant, that is the mass won't change. Now I'll get the separate equations for heat added, heat subtracted. I'll start with heat added. The first thing, that heat added at constant pressure is given by, it is Q suffix A, and since the heat is added at constant pressure, so it will be M Cp, and as we know heat is added from point 2 to point 3, that is it is from 2 to 3, so the temperature difference will be the higher temperature, that is T3, minus the lower temperature T2, that is the temperature difference. So it will be MCP T3 minus T2, and as we are assuming the mass to be 1 kg, so therefore QA will become Cp T3 minus T2 into the bracket. I'll write down, since M is equal to 1 kg which we have assumed, so here I will keep this heat added as my equation number 1. So now once I have written it for heat added, now I'll even write it for heat rejected. So heat rejected at heat added was at constant pressure, heat rejected is at constant volume. So heat rejected at constant volume is given by Q suffix R is equal to M, and it is constant volume. So MCV, heat is rejected from point 3 to 4. So the temperature difference will be higher temperature minus lower temperature, that is T3 minus T4. And if we see, it would not be T3 minus T4, actually this is the expansion process. Heat is rejected from 4 to 1. As we can see, from 4 to 1 the heat is rejected. So the temperature difference will be T4 minus T1, not T3 minus T4. So here I'll mark it as, this is T4 minus T, here we are having T4 minus T1 as the temperature difference, higher temperature minus lower temperature. So it will be T4 minus T1. So therefore heat rejected is equal to CV T4 minus T1, and here also I'll write down, since mass M is equal to 1 kg, and this I will keep it as equation number 2. Now if we are adding some amount of heat, and from that if we are rejecting some amount of heat, then the difference, that is QA minus QR, that would be called as the work which we are getting from the system, that is the work we are getting during the expansion process. So here I'll write down, therefore work done in expansion is given by, now that work done in expansion I'll denote it as WD, and it will be QA minus QR, heat added minus heat rejected. So therefore work done will be equal to, now heat added we have written, it was Cp T3 minus T2 minus heat rejected, it is Cv T4 minus T1. Here I'll say that refer equation number 1st and 2nd. So therefore work done will be, I'll write it as, it will be the same thing, I'll keep it as it is, Cp into T3 minus T2 minus Cv T4 minus T1. I'll keep it as it is because I won't make any changes here. Now after we have reached from heat added at constant pressure, heat rejected at constant volume, then work done, which is heat added minus heat rejected. Now I will write the formula for efficiency. I'll write down efficiency of diesel cycle is given by, the general formula of efficiency will be work done upon heat supplied, that is the heat added. So therefore efficiency of diesel cycle will be equal to, now work done is Cp T3 minus T2 minus Cv T4 minus T1, then heat added, it is at constant pressure, so it was Cp T3 minus T2, as we have seen previously, the heat addition process at constant pressure, Cp T3 minus T2. So therefore I'll write this as efficiency of diesel cycle is equal to Cp T3 minus T2. I'll keep it as it is in the numerator. Now this denominator is common to both the terms. So here I'll write down Cp T3 minus T2 minus Cv T4 minus T1 as it is divided by Cp T3 minus T2. I have taken the denominator common through both the terms. Now if we see here, Cp and Cp will get cancelled out. T3 minus T2 and T3 minus T2 will get cancelled out from the numerator and denominator. So 1 remains here. Next, I'll reuse the relation, that is first I'll write it as it is. Therefore, what remains that I am writing, efficiency of diesel cycle will be equal to 1 minus. Now Cv upon Cp into T4 minus T1 upon T3 minus T2. Next, therefore, efficiency of diesel cycle will be equal to 1 minus, now I'll keep T4 minus T1 as it is, Cp, this Cv I'll send into the denominator, so Cp, this Cv I am sending here, so Cv comes into the denominator, it is one and the same thing, T3 minus T2. So therefore, efficiency of diesel cycle will be equal to 1 minus T4 minus T1 upon Cv is denoted by gamma, T3 minus T2. Now I'll keep this as equation number A, and here I'll write down that since the ratio of Cp upon Cv, it is called as gamma. Now after we have arrived here, next I'll take the processes as it is, that is starting with process 1 to 2. Now as we see, process 1 to 2 is isentropic compression. So for that I'll write down that since for process 1 to 2 as it is isentropic compression, so for that we can write down T2 upon T1 is equal to, it is V1 by V2 raised to gamma minus 1, and it is also equal to P2 by P1 raised to gamma minus 1 upon gamma. But here I'll utilize only the first part of this relation, that is temperature and volume. I am going to utilize only this much part. Then as we can see here, T2 by T1 I'll keep it as it is. Now V1 by V2, see V1 is called as the volume before compression, that is if I see it on the PV diagram, this volume before compression process, that is V1, and volume after compression is V2. So V1 upon V2, that is the relation, and it is called as compression ratio. So here what I'll do, I'll replace V1 by V2 by a term called as R suffix C, and it is raised to gamma minus 1, and into the bracket I'll write down, since RC is called as compression ratio, and this compression ratio is equal to V1 by V2, that is volume before compression and volume after compression. So now here I am getting the relation of T2 in the form of T1 and compression ratio. So I'll say that therefore T2 will be equal to, I'll send T1 onto the other side, T1 into RC raised to gamma minus 1. Here I am getting the relation of T2 in the form of T1 and RC. Next, I will be keeping this as equation number third, because we have reached up to equation 2, so I'll keep it as equation 3. Next, as we have seen for process 1 to 2, now for the next process, that is for process 2 to 3, which is constant pressure heat addition. Now for constant pressure heat addition process, I'll write the equation for process 2 and 3. It can be written as P2V2 upon T2 is equal to P3V3 upon T3. This term, or we can say this is the state equation which we can write for any one of the states. So here as we see, for state number 2 I am writing P2V2 upon T2. For state 3 I am equating, because at both the states the total amount should remain same. So here I am writing P3V3 upon T3. Now as we see, since it is constant pressure process, so P2 is equal to P3. So from both the sides P2 and P3, it will get cancelled out. And here I have to mention that since pressure at point 2 and pressure at point 3, they are same. Next, therefore I will shift T3 here. So T3 is in the numerator, and then in the denominator we have T2 is equal to V3 is in the numerator, V2 will go into the denominator. Now here V3 upon V2, it is called as fuel cutoff ratio. That is, if I can explain it on the diagram, here if we see at point number 2, the fuel, we can say it is burning, it starts burning at point number 2, and that heat addition continues up to point number 3. So at point number 2 the volume was V2. At point number 3 where the fuel is cut off, means fuel supply stops at point number 3. So this is the fuel cutoff at point 3. Here this is the fuel cutoff. So the volume at fuel cutoff and the volume where the fuel spraying, or we can say the fuel addition starts, this ratio V3 by V2, that would be called as fuel cutoff ratio. So here I'll write down that V3 by V2 is equal to rho, and into the bracket I'll write down, since rho is called as fuel cutoff ratio, and this fuel cutoff ratio is V3 by V2, that is the volume at fuel cutoff to the volume before the fuel addition starts. Next, therefore T3 will be equal to, I'll send T2 onto the other side, so T3 will become T2 into rho. Next, from equation 3 we have the value of T2 that I am going to put here, so it will become T3 will be equal to, now T2 is T1 into RC raised to gamma minus 1 into rho. So here I have this value of T3. I'll keep this as equation number 4. Next, for process 3 to 4, which is the isentropic expansion, or in other words it is reversible adiabatic expansion. So I'll write down for process 3 to 4, that is reversible adiabatic, or it is called as isentropic process. Now for this process 3 to 4, here I will write down, it will be T3 by T4, as I have written previously T2 by T1 for compression. So here I will write down T3 by T4 is equal to, it will be V4 by V3, V4 by V3 raised to gamma minus 1, and that is also equal to P3 by P4 raised to gamma minus 1 upon gamma, but here we are interested only in the temperature and volume relation, so I'll use only this first term. So as previously I have written, for the compression process it was T2 by T1 is equal to V1 by V2. Here I am writing T3 by T4 is equal to V4 by V3 raised to gamma minus 1. Next, therefore T3 by T4 will be equal to, instead of V4 I'll write down it is V1, because as we see, volume at point number 1 and volume at point 4 both are same, so I am replacing V4 with V1. So V4 has been replaced, and next here I'll divide and I'll multiply by V2. So in this step, as we can see, V2 when gets cancelled, so we will get the same term. So here I am multiplying and dividing by V2. I'll write down that multiply and divide by V2. So therefore T3 by T4 will become, now V1 by V2. We know that V1 by V2, that is called as compression ratio, RC, and it has been written, yes, RC is the compression ratio which is V1 by V2, so that I'll replace it with RC. Then V2 by V3, see V3 by V2, V3 by V2 is fuel cutoff ratio. So if I write V2 by V3, this rho will come into the denominator, that is, therefore if I write it in the reciprocal form, so 1 upon rho, it will be V2 by V3. So the same thing is happening here. Here we have V2 by V3, so rho will go into the denominator raised to gamma minus 1. Next, after reaching at this stage, since we want T4, up to T3 we have reached, so I'll bring T4 on the other side and this entire term into the denominator. So we have, therefore T4 will be equal to, in the numerator we will be having T3, in the denominator we will have RC upon rho raised to gamma minus 1, RC upon rho raised to gamma minus 1. So therefore T4 is equal to, now T3 value we have in equation number 4. This T3 I'll write here, which is T1 into RC raised to gamma minus 1 into rho. Next, the terms which I have here, even RC, I'll open the bracket here, that is RC, outside the bracket we have gamma minus 1, so it will get gamma minus 1 upon rho raised to gamma minus 1. Next, I'll simply shift the terms, that is T1 I'll keep it as it is, RC raised to gamma minus 1 as it is. Now when I shift this term, that is here I am getting RC raised to gamma minus 1 in the numerator, so that will become, it would be with a negative sign, so RC minus gamma minus 1. Next, here I have rho, and this rho which I send it into the numerator, so that will be rho raised to gamma minus 1 as it is. Now if I see here, this is RC raised to gamma minus 1, this is RC raised to minus gamma minus 1, so both will get cancelled out and this term here 1 will be left. Next, it is rho which is raised to the power 1, and here we have rho raised to gamma minus 1. So now here I have written that rho is raised to the power 1 and here we have rho raised to the power gamma minus 1. So on simplification this will be rho into this is 1 plus gamma minus 1. So plus 1 minus 1 will get cancelled out and we will have rho raised to gamma. So on simplification T4 will become, here it is T1 into rho raised to, this entire term is rho raised to gamma. So I'll keep it as equation number 5 after getting T4. Now once we have all the temperatures, we can put their values in equation number A, that is the efficiency of diesel cycle. Here I'll put the values of T4, T3 and T2. So therefore put values of T2, T3 and T4 in equation number A. So it will become, therefore efficiency of diesel cycle will be equal to 1 minus, now in equation A we were having, it was 1 minus T4, 1 minus T4 minus T1. So first I'll put the value of T4, and T4 is T1 into rho raised to gamma minus T1 divided by, in the denominator here we have gamma, which I'll keep it as it is, and it is T3 minus T2. So I'll go on putting the values of T3 and T2. Now T3 and T2 values. So T3 is, it is T1 into RC raised to gamma minus 1 into rho, T1 into RC raised to gamma minus 1 into rho. This much value is of T3. Next T2, it is T1 RC raised to gamma minus 1. So minus T1 into RC raised to gamma minus 1. Here I'll say that since refer equation number 3, 4 and 5, where we have the values of T2, T3 and T4. So next, as I can see here in this efficiency of diesel cycle simplification, here T1 is common in the numerator. So T1 I can take it common. Then we will have rho raised to gamma minus 1. Then in the denominator we have gamma. Here again T1 I can take common. And next we have RC raised to gamma minus 1 into rho minus RC raised to gamma minus 1. So from numerator and denominator T1 will get cancelled out. Next, here we have RC raised to gamma minus 1, RC raised to gamma minus 1. It is common in the denominator, so I can take it common. So efficiency of diesel cycle will be equal to 1 minus 1 upon RC raised to gamma minus 1. In the numerator rho raised to gamma minus 1, and here in the denominator we even have gamma, so I'll write gamma here, and into the bracket we are left with rho minus 1. So almost we have reached up to the final stages of the derivation. So next, therefore efficiency of diesel cycle will be equal to 1 minus, I'll keep this term 1 upon RC raised to gamma minus 1 here, and then gamma I'll multiply it inside in the denominator, numerator will be rho raised to gamma minus 1, and here I have gamma into rho minus 1. So this is the expression which we have derived. I'll keep it as equation B. So therefore I'll say that from equation number B, efficiency of diesel cycle can be calculated. And here we can see that diesel cycle efficiency is dependent on two terms, that is RC, which is the compression ratio, and rho, which is called as fuel cutoff ratio. And here in this video we have seen the efficiency formula for the diesel cycle and how it is derived.